Hi everybody, today we are going to prove the power rule, which will allow us to find certain derivatives a lot quicker and easier. And then we're going to do a couple problems that will allow us to use this derivative. Okay, so first of all, this is the power rule. So if you have a function f of x equals x to the power of n, we can find the derivative using it's like a little shortcut. Essentially, what you do is you take the exponent and you multiply it to whatever coefficient is right here. That's where this n comes from in front. So once again, you take the exponent and you multiply it to whatever coefficient is in front of x. Then the degree of your variable decreases by 1. So that's what this n minus 1 means. So once again, you take the exponent, multiply it out front, and drop it down by 1. And that is going to be your derivative. Here's just another way that we can notate derivative rather than using f prime of x, we can say d dx. But for us to be able to use this power rule, I want to make sure that we can prove the power rule. And that is going to involve us using the binomial theorem, because we're going to do a little bit of binomial expansion. So just a quick reminder, for any term, when you're doing binomial expansion, any term can be found with this formula. And this would be if you had x plus y to the power of n. Any term can be found with this formula, where r is 1 less than its relative position in line, and n is the degree of your binomial. So now we are going to be using this, and we're going to prove this power rule. So we're going to find a derivative of x to the power of n using our limits, just like we've done in the past. So we're going to do the limit as h approaches 0, and we're using this function, x to the power of n. So we're going to start with f of x plus h, so that would be x plus h to the power of n, minus f of x, which is x to the power of n, all over h. So now we need to find this limit. And we know that when we found limits in this way in the past, the next thing we would do is multiply out this binomial and combine like terms. So for us to be able to multiply out this binomial, we're going to use binomial expansion. So let's take a second and do that. When we multiply out the first term is always going to be x to the power of n. Then as we progress, we can use this to help us find the coefficient, but essentially the x degree is going to decrease in value and the degree of h is going to increase in value. So if we do n choose 1 for this next spot, it equals n. So we have n to the power n times x to the power of n minus 1. X decreases in value and h starts increasing. So we have h to the power of 1. Let's see if we can describe another term. Here we'd have n choose 2, that's our r value, times x to the power of n minus 2, it drops down again, and h increases by 1. So here we had h to the power of 0, h to the power of 1, h to the power of 2. Now let's say we just jump ahead to some term in the middle, our general term. So I'm going to use that general formula and choose r, x to the power of n minus r, h to the power of r. And let's jump ahead to our second to last term. Our second to last term will always have the same coefficient as our second term. So n, and then x is going to be to the first degree because it's almost out of degrees. It's decreasing until it doesn't exist anymore. And then h has almost maxed out. And then our last term, oops, sorry about that. Our last term is just going to be h to the power of n. So we did binomial expansion, and this is equivalent to all of this. But you can see that we still have minus x to the power of n, and then it's all over h. So now our next step would be to combine like terms. So we see that this x to the power of n and negative x to the power of n would cancel out. Our next step in finding this limit would be to divide out a common factor, and I see that all of these terms have at least 1 degree of h, and there's an h in the denominator. So we're going to divide out h, and then see if we can evaluate the limit from there. So if I divide out h, this first term, my h disappears completely. Then I have plus all of this. Now it just becomes h. H to the second power has been reduced by 1. We can even rewrite that middle term. So this will be h to the r minus 1. And let's jump ahead to the second to last term. So n times x times h to the n minus 2. So it drops down 1. Plus h to the n minus 1. So that also drops down 1. Now this is something that I can evaluate using direct substitution. So I'm going to use direct substitution for h equals 0. And what you'll notice is that any of the terms that have an h left are going to turn to 0. Therefore, all of these terms are going to disappear. And what I have left is n times x to the power of n minus 1, which you might notice is the formula for the power rule, which is right here. So there you have it. This is the proof for the power rule, and now since we proved it, now we can use it. Okay, so here we are asked to find an equation of the line that is tangent to f of x and is parallel to this line. So now you'll see that finding the derivative is just going to be a tiny quick part of this entire problem. So whenever I'm stuck or I see a problem that looks a little bit challenging, I'm always going to look for words I know, like parallel. So I know that parallel means that it has the same slope. And of course, anything having to do with slope will be your derivative. So if I look at the slope of this line, I see that the slope is -2. So I'm wondering, where in this function is my slope -2? So when is the slope of f of x -2? And so I'm pretty much wondering, when is f prime of x equal to -2? Because f prime of x is the slope of f of x. So I'm going to need to find f prime of x, and for this we can use that power rule. So f prime of x equals, I take my coefficient here and I multiply it, my exponent, which is 2, and I multiply it to the coefficient, which is 1. 2 times 1 is 2. And then my degree decreases by 1, so it becomes x to the power of 1. Here you can think of this as 1 times x to the power of 0. If you multiply 0 to your coefficient, it disappears. So this is our derivative. So we're wondering, what x value makes the derivative -2? Because that is the slope. So -2 equals 2x. So that is occurring when x is -1. So I do want to point out that in the past, when we've been using our derivatives, we are given an x value. So we say, for this x value, what is my slope? But it works the other way as well. We can say, here's my slope. At what x value is that occurring? So it's occurring at the x value -1. But if we want to make the equation of a line, I'm going to need to know the full coordinate. This is just the x value. So I need to find f of -1. So I'm going to go back to my original function, because remember, I'm finding the point on this function where my slope is -2. So f of -1 is 2. So when is the slope of f of x -2? At the coordinate -1, 2. So now I have a point, I have my slope, I can use point slope formula, y minus y1 equals m times x minus x1. And if I put it into slope intercept form, it's just y equals -2x. And there you have it. Okay, so go ahead and pause the video and give this one a try. All right, so we're essentially wondering at what point, or at which 2 points, is the slope of my function equal to -6, because it has to be parallel to this line. So first I'm going to find the derivative, which is -3/2 x squared, and I'm wondering, when is my derivative equal to -6? For what x values does my slope become -6? So here, if I solve for this equation, you'll see that we actually get two possibilities. We have x equals positive or negative 2. So we can actually make an equation for each of those. So I need to know the full coordinate. So f of positive 2 is negative 4. So here's one point where the slope is negative 6. F of negative 2 is positive 4. So here's the other point. Just so you guys know, the reason why there's 2 points for this one, if you look at our original function, it's a negative cubic function. So it looks something more or less like this. So there are 2 points in time where our slope can be negative 6. In fact, here our slope is always going to be negative, but it's happening twice due to the shape of that cubic function. So that's why we have 2. And then from here, you can use the slope and your point, and you can create your 2 equations for those tangent lines. All right, so now we're going to use the derivative to determine any points on our graph, this f of x, at which the tangent line is horizontal. So I want to know what we know about horizontal lines. And what we know is that horizontal lines have a slope that is 0. So I'm essentially wondering, where is the slope of f of x 0? Because that's where the slope of the tangent line is 0, which is where it's horizontal. So that's another way of saying, where is f prime of x, our derivative, 0, because the derivative is the slope of the original function. So let's find f prime of x using our power rule. We're going to take our exponent and multiply it here, so 2, and then our exponent decreases by 1. 2 minus 1 is 1. Here I take my exponent, which is 1, and I multiply it to the coefficient, so we get negative 6, and then my exponent decreases by 1, so I have x to the power of 0, so no x. And then this 4, this constant is just going to disappear, so this is our derivative. Now we're wondering, when is the derivative 0? When is the slope 0? For which x value? So I'm going to set our derivative equal to 0, and that occurs when x is 3. And we need to know the full point, so we're going to find f of 3, essentially substitute it here, and we get negative 5. So the coordinate where that occurs is at 3, negative 5, which is, in fact, our vertex. So you guys are going to start to notice that your tangent line is going to be, the slope of your tangent line is going to be 0 when you have some sort of turning point in your graph. Any type of absolute or relative, minimum or maximum, is when your slope is going to be 0. All right, last one. Go ahead and pause the video and give it a try. Okay, so here we want to know when our derivative is equal to 0, or when our slope is equal to 0, the slope of our function. So the derivative is 3x squared plus 3. So I set that equal to 0, and if I try to solve for x, we'll notice that we get an imaginary answer. So that means that our derivative is never 0, which means that our tangent line is never horizontal. So one reason why this is happening, once again, this is a cubic function, and it's a positive cubic function. This, the slope of f of x is actually always positive. It never has a turning point, so the slope is never going to be 0. Another thing you can look at is your derivative. This derivative is a function as well, and this function is a parabola that's above the x-axis. So we see that our slope is always going to be positive, and therefore it will never be 0. So in this case, we never have a tangent line that is horizontal. All right, that is all for today's lesson. Thank you so much for watching.